So, so first thing first, as you might have noticed from the references, this is not like a pure proper math talk because the references are not what I would call math books. It's just supposed to be a more informal thing where I give you the intuition for a lot of cool stuff in geometry. And so so the first ground rule that I would like to set is that if there is something that you know or are quite familiar with, and if I ask a question on that, then please let everyone have a fair shot to think about it and don't answer immediately. So we'll start with the word geometry. What I would like to ask you guys, what do you think of? What are the main things that you think of when I just write the word geometry? Shapes. Good. I'll just make a list.
Presenting ideas in spaces.
Presenting ideas in space. What?
Measuring distances.
Sorry?
Measuring distances.
Okay. Measuring distances. So this is actually quite similar to the definition of geometry that you'll find on Wikipedia. It says that geometry is a branch of mathematics concerned with the properties of space such as the distance, shape, size, and the relative position of figures. So I guess it's just a longer way of elaborating on the key points that you guys have mentioned. Now, in order to talk about any geometry, I need to know that you know what a manifold is. So how many of you know what a manifold is? Okay. So the definition of a manifold is just that, locally, when you look at a small enough patch of your space, then it is similar to Rn, which is a normal Euclidean space. And this n is called the dimension of the manifold. So a two-dimensional manifold would be a surface. So anything that when you zoom in enough, it looks like the plane R2. Anyone wants to give me examples of manifolds?
Sphere.
Spheres.
So
Good.
can there be manifolds which have different dimensionality at different points?
That's a good question. Usually, as far as I know, we consider them to have the same dimension. But if, yeah. So the thing is, yeah, if your manifold is disconnected, you could consider like a sphere and a disjoint. So a sphere and a disjoint line. Well, it's up to you if you want to call this a manifold. So yeah, that just depends on your definition of a manifold if you want to allow for such things to happen. Now I will start with the story. So yes, that's where the first reference comes in. So this is a tale of creatures living in two dimensions. So the space that they live in is two-dimensional, unlike our space, which is three-dimensional. So the things that they observe are essentially one-dimensional. Like if like the way I'm looking at you right now, it's a two-dimensional image. I can't see all parts of each of your bodies at once. I can only see the front. So similarly, these two-dimensional creatures have such restrictions that when they just look in front, they see a one-dimensional object. And the creatures here, they are different shapes. There are triangles, there are squares, there are circles, and our story is going to focus on one specific triangle. Called T. This is her picture. So yes, T. She is a very a curious young individual, and she has excelled in all her geometry courses that have been taught to her in school. But of course, she aspires to learn more about the space that she lives in. So this is actually quite similar to one of the main problems that we have in geometry, which is classifying manifolds. So by knowing certain properties of a manifold, you want to learn what class you can put it into. And when can you say certain manifolds are different? When can you say that they're the same? So, suppose T wanted to find out more about her manifold. She wants to find out what is the nature of the space that she lives in. Then what kind of clues can she use? So, before I elaborate, I will show you what I mean when I say an intrinsic property and an extrinsic property. So an extrinsic property is a property of a space that it attains by being embedded into a bigger space. So, and that's just a fancy way of saying that, well, this sphere that you're looking at is in 3 dimensions. And let me think of a better way to put it. We consider this napkin. Now, this red line, if I hold the napkin entirely straight, then it's like a straight strip. But when I am curving it, if I hold it like this, then this same red strip becomes curved. So the property of this line being curved is sort of an extrinsic property. So the extrinsic nature of this line has changed. But if you imagine T to be living on this napkin, inside this napkin in fact, not on the surface of it, but inside it, then I would like to ask you, would she be able to tell the difference when this napkin is flat compared to when it's curved like this? How many of you think yes?
Is there gravity there?
Sorry?
Is there gravity on the napkin?
Well,
The argument similar to maybe flat earth.
yeah,
It depends on.
I don't think it impacts the situation whether
But like, if it is curved,
Yeah.
the person is climbing it, they will feel a potential difference. It will be difficult to climb one side and go down the other side. Then they'll know that it is curved.
so you're saying there's some sort of gravity distribution which is like, what is the gravity being caused by? Like if it were an equal downward force everywhere, then she would not be able to tell the difference. But yes, if it were a property of the napkin, maybe. That's an interesting idea though, yeah.
It depends whether she is microscopic or macroscopic respect to the shape of the napkin. If
Oh,
she's like really small with respect to it, then like maybe she won't get if it's curled or not. But if the relative size is almost similar, she will get easily that the napkin is curled.
May I ask why you think so? Like
Because,
why do you think the relative size matters?
Because if the size of T is almost, if you can say, even 1/8 of the napkin, she will get that it's curled because the curl will be visible to her.
See, this is, yes, so the fault in your argument is that you are imagining T is standing on top of this napkin. The same way we are standing on top of the earth. But we are living in three-dimensional space. She is living inside the napkin. That's what I want you to imagine. So, well, if I were to draw her, it would look like this. She would be embedded inside the napkin and she can only move constrained to the napkin. She does not exist outside of it.
So we are like curving the space around her.
Yes.
Okay.
Yes, that can also go deep.
Yeah,
that
it
will
would
also
curve.
come T because
Yes.
of the sound.
Definitely. But would she know that she's curved?
No, now I think she won't know.
Yes, you're right. So, mathematically, how I would say this is that this curved thing is actually isometric to the flat thing, which means they have the exact same geometric properties. But instead, if suppose she suppose she lives on a napkin and suddenly that napkin transforms into a hemisphere. Not a very good hemisphere. But then do you think she would be able to tell that anything has changed? How many of you think that she'll be able to tell? Okay, how many of you don't think she'll be able to tell the difference? Okay. Anyone who would like to vouch for their stand?
So she'll be able to tell the difference, because if she is walking away at right angles on two different paths, in the flat case she'll never come back to the same point, like to a common point. And in the hemisphere, she will come back to the antipode, right? Like assuming she starts at the rim.
It's a hemisphere, it's not a sphere. Where will she come back?
Rim to rim. Works. There's still a rim to rim.
Oh, so you. How is she walking?
At the rim, there's two paths moving at right angles to each other. And then
At the rim, here.
Yeah.
Right, okay.
Imagine it more towards the center of the rim. You get
Yeah.
it? Yeah. And two paths going off at right angles.
At right angles.
Yes.
So here and here.
Yeah, that also works. So the
And-
path that's going up will come back to the rim, and the path that's going to the right follows the rim.
I see. So you're trying to use the boundary of the surface to identify what kind of surface she's on. That's actually a decent idea, but even if she was on a square which had a boundary, if she goes like this, she go like this and she come back here, and she goes like this, again she'll end up at another point on the boundary, right? So I'm not sure she'll be able to simply tell the difference like that. But in fact she will. She will be able to tell the difference, and I'll show you how later, soon. So let's come back to what kind of properties T can think about for her space to be able to understand it better. So one of the properties is something that you had mentioned, measuring distances. So have you all heard of what a metric space is? Okay, so a metric space is just a space with a distance function that satisfies certain property. But yeah, the main thing is just that it's giving you a distance between any 2 points on the space. So do you guys have any ideas for how T would try to measure the distances between 2 points on her space? Well, yeah, it's not.
Minimum distance. Minimum distance. Whatever is the minimum distance for a given path.
Yes. So what T can do is, I'll draw something bigger. Suppose this is her space. There's a point P and a point Q, and she wants to calculate the distance between these 2 points. Then she takes a path. At first, a random one. So imagine T going along this path. Then she takes another path. And another path. So if she only had a finite amount of time, this would probably not get anywhere, because there's an infinite number of she can take. But assuming that she has all the time in the world, and assuming that she can actually travel at a constant speed, then can you tell me how she would find the distance between P and Q?
The path which she takes, the path from P to Q which takes her the least amount of time.
Yes. So the length of these paths, if we assume that she is traveling in constant speed, then the length of these paths is directly proportional to the amount of time that she takes. And yeah, it turns out for manifolds, for most nice manifolds, the distance between 2 points is equal to the length of the shortest path between them. In this case, can anyone tell me what the shortest path is?
Straight line.
Yes. So, given an infinite amount of time, T figures out that this is the shortest path between 2 points on her manifolds. And this shortest path is something called a geodesic. Now, the study of these shortest paths themselves can tell us a lot about the manifold. So, given that you guys were able to tell me here what the shortest path is, I'm assuming you will also be able to tell me what the geodesics are for any space Rn. What will they be?
Straight line.
Straight lines. And yeah, so when you study straight lines in Euclidean space, they have a lot of properties. Like you can have lines which intersect. You can have lines which don't intersect. You can have lines which like extend off to infinity, which are unbounded in some sense. But what if now you think about the geodesics on a sphere? Does anyone know the geodesics on a sphere? Which circle? Yes. So it turns out that the geodesics on a sphere are great circles. Great circles are circles which have the center of the sphere as their center. So circles like this. So both of these circles are great circles. And in order to find the distance between any 2 points on the sphere, you just have to check which great circle they're a part of, and you measure the length of that segment. Yeah.
Is there always a great circle that passes through both of the points?
And you're asking for a proof. I didn't do that here. But yes, it can be proved. So the sphere is something called a geodesically complete space. And there's a theorem which says that in any geodesically complete space, there will be a unique geodesic between any two points. and that geodesic can be defined on all of R. But yeah.
Antipodal points will have a lot
Sorry?
of geodesics. Antipodal points
Yeah.
on the sphere.
Yeah.
They'll have an infinite number of geodesics. How does the film hold that?
Right. So my bad.
No.
Yeah. So he said antipodal points on the sphere will have an infinite number of geodesics passing through them. So how will there be a unique one? Yeah. I'm pretty sure there's some subtlety involved in the statement. But I'll get back to you after this.
I just asked whether there exists a geodesic.
Yeah. Yeah, but still, like, yeah. Yeah. So, now, to rule out certain possibilities of what the space T lives in can be, T decides to walk along a geodesic and for as long as she can. So she chooses a direction. She starts at a point P, she chooses a direction and continues to walk along that direction with a constant speed. And she realizes that after some point, she is right where she started. She has arrived at P again. So is it possible that she is living on a space like this? No. Naturally. So that tells us that, well, maybe she could be living on a sphere. But
Can't we go around the square? Around the square.
how would you go around the square? Like,
Because this is the square, it goes like this, and it goes like this.
oh, so yes, so the fallacy in that point of view is that you are assuming the square has some thickness. And this is something people very often do, but it's good that you brought this up. So a true square is when it's two-dimensional, it has no thickness at all. So a square doesn't have two sides. It doesn't have a front and a back. It only has a front and a back if it's a piece of paper, if it has some thickness on it. But if it's a true manifold, then there is no notion of even a front or a back side of it. It has truly zero thickness. That's what you have to imagine.
Back to your question, what you said about she can't find herself back at the same point if she's going in a straight line.
Yeah.
Right? So I can think of that you would allow that as sort of a Mobius strip. But would that also fall under what you're saying that it can only exist if it's embedded in a 3D space sort of thing? Like can you think of a Mobius strip without thinking of it as a piece of paper in a 3D space?
Yes, you can actually.
So then would
You-
that work here?
Yes.
So what is
So, so you can always think of a manifold in of itself without referring to the ambient space that it is in. And yeah, if you want to talk about a Mobius strip, then there are multiple ways to embed it into a space that we already know. So one of the ways is to just draw the Mobius strip in 3 dimensions. Take a piece of paper, twist one side, stick it back to itself, and you get a Mobius strip. And another way to visualize it is looking at this same square strip, but sort of gluing this line with this line. So each line over here, each point over here is glued to this point. So it's the same as doing the twist, but you can just imagine it in 2 dimensions as well, in some sense. But when I drew this, I was not talking about any identifications. So clearly you can't just have a square to be your space. So at least the triangle now knows that her space does not look like a bounded square. So it could look like a sphere. It could even look. It could look like a Mobius strip. It could even look like a cylinder, because she could have. She could have traveled in this way, and yeah, ended back where she started. But in the beginning, I told you when you can differentiate a sphere. I told you how T can distinguish between a hemisphere and a flat piece of paper. So I'll now come back to how she can do that. So one of the things that you guys did not mention when I was talking about geometry in general was angles. Angles are an important part of geometry. So T will definitely benefit by being able to use them. So we consider this hemisphere, and suppose now we are assuming that T knows all the geodesics in her space. So she goes along a geodesic like this. And suppose she reaches the edge. Then what is this angle? 90. Now she travels along another geodesic. This is actually a geodesic, right? Because it's a hemisphere. And she reaches a point over here. And then she travels along this path. So what is this angle? And this angle? Ah. So there we have it. We have a triangle on the hemisphere whose sum of angles is 90 plus 90 plus 90. Could this happen on a flat plane? No. And how does she know they're 90 degrees? Or she can just turn. But yeah, if you wanted to actually precisely answer how she can measure angles, then you'll need a lot more machinery. You'll need to define the tangent space of a manifold and then put an inner product on that tangent space.
Her shape.
Sorry?
Her shape.
Her?
Shape.
Her shape.
Yes. Itself as a
Yeah. So you want T to use her own shape to measure angles. That's an interesting idea. Yeah. Yeah, I guess she could. If I knew this was a perfect 90, I could just. Yeah. That's good. So this tells us that there can be manifolds where the sum of angles of a geodesic triangle is not 180 degrees. And in fact, whenever it's greater than 180 degrees, usually the space is positively curved, which means that it's sort of curved outwards. Whenever it's not curved at all, or more precisely the Gaussian curvature is 0, then its angle sum would be 180 degrees, like in the Euclidean space. And as I have learned from my from my MS project, when the space is negatively curved, and an example of this is the hyperbolic space, which has negative curvature everywhere. It's like you can imagine it being curved inwards. Then the geodesic triangles will have angle sum less than 180 degrees. And one interesting side thing that I learned in my project was that it's not just less than 180 degrees. So for hyperbolic space, the sum of angles of a triangle in hyperbolic space is 180 degrees minus the area of the triangle. Does this look weird to you?
Dimensions.
Sorry?
180 degrees is a dimensionless quantity. Area is a dimensional quantity.
Yes. But okay, I should say pi then. No?
Sure, but yeah, area still has units.
I don't think that matters. Like,
maybe we could add like have a coefficient of area as a dimensional constant having a value 1. A dimensional constant having a value 1 could be a coefficient of that. Could be a multiple.
so yeah, so when you do math, you will actually forsake all the sort of dimensional analysis that you're doing. But
Get that.
yeah,
But it still applies here.
it need not. It applies in a very specific context that you learn it in, right? The units of measurement.
But like then you are defining some units here as well.
Yes, so, but yes, so that's what in math the definitions can be so weird that you won't really concern yourself with that.
So how do you define the area here?
Sorry?
How do you define the area of a triangle here?
Oh, you have to do it by integration. You have to define something called a volume element, and then you integrate along that triangle with respect to that volume element.
I'm guessing the area will never be more than pi.
Well, from this, yes, it would be strictly less than pi, because angles are always positive.
Is this the area in the projection of the hyperbolic space? Or does that remain constant?
Area in the projection, is it?
So if we project it onto the circle in the xy plane, the half the hyperbola, that gives us like the
Right.
circle's area, the unit circle's area is pi. That would make sense that an infinite triangle has like pi area and the sum of angles is 0.
Sorry, I didn't quite get your question.
So a hyperbola, a half leaf hyperbola can be, sorry, one leaf,
One leaf.
surface.
Okay.
Just the top half. That is what I mean.
Yeah, the half plane. You mean? Yeah,
Whatever.
yeah. Sure, yeah.
So it can be projected onto the unit circle, right? If we
Yeah.
if we define the area of the triangle as the area in that projection,
Okay.
the maximum it can be is pi.
Okay.
That solves the unit issue.
I haven't seen it be defined that way. Like I've seen this. Yes.
What's the biggest triangle you can make in hyperbolic space?
A triangle that has area
That has
pi.
areas, I agree, but how?
You can't have area pi, right? Because the angles have to be positive. No, angles can be 0. Sorry. Yes.
You are saying that a
So-
triangle that has no area will have its angle sum as pi.
An infinitesimally small triangle would
Sure.
just be a triangle in R2.
Then at that point, will you even call it a triangle? No, we're saying the opposite. He's asking for the maximum
No,
area.
yeah. Sure. Then
So
mine is a different
all
thing.
the triangle. Oh, okay. Yeah, different question. Right. Well, yeah. If you reduce a triangle to a point, then I'm not sure if you would still call it a triangle. It becomes a very limiting case. Yeah.
How exactly are we defining the area of the triangle? Because when we are making a triangle in a hyperbolic space, so as much I am having the knowledge of that hyperbolic space, there won't be any enclosed area. Or am I wrong in some way?
Okay. I'll just draw a hyperbolic triangle for you. This is a hyperbolic triangle, and this is the enclosed area. So in the hyperbolic space, semicircles are geodesics. So each of these faces is a geodesic segment. So you can see. Does that answer your question?
I don't know. What exactly is hyperbolic space? I don't know which part of the hyperbolic space we are talking
Draw
about.
the hyperbola and show.
Which part of?
Like hyperbolic space is that now when we are like drawing a hyperbola and then like
Right. Yeah. So there are multiple models. There is one model of the hyperbolic space where you draw the graph of a hyperbola and you rotate it
Ha ha ha.
to get a surface.
Yes.
So in that, yeah, again triangles would look slightly different. But if you were looking from the bottom, then your triangle would actually look like. Oh, okay. Yeah.
Well, yeah, that is a closed hyperbola.
Yeah, these things are sometimes difficult to imagine. Yeah, this is the model that you're talking about, I
Yes.
believe. Yeah. On
Close
this,
to this, we are having this curve.
He's talking about the.
I'm talking about this one.
oh,
And
I
we are
haven't.
having the points here, here. They have shown it like this. I don't know.
Oh.
in Google. And thought of the points here, here, and here.
Okay.
And
I
then-
actually haven't ever seen this model of hyperbolic space.
Oh.
But, okay.
I just thought it as a hyperbola in 3D.
Yes.
It's a different
So,
rotation.
this is a hyperbola, right?
Yes.
And you rotate it.
Oh, it's just an axis. Okay. Oh,
Yeah.
okay. This axis.
Yes.
Yeah, I got it.
So anyway, this is a digression. But yeah, so by using such arguments about angles, T can tell whether her space is curved or not. And so she draws triangles on her space, geodesic triangles on her space, and it turns out that the angle sum is 180 degrees. So it's not in fact a curved space. Maybe I'll just write down her observations till now. Yes.
If you have a space where every triangle necessarily has angles from 180,
Yes.
can you say something like it is isometric to this project?
So the question is that if the angle sum is 180 degrees everywhere, then can we say that the space is isometric to Euclidean space? No, I don't think you can. But you can conclude. Yeah, I believe you can conclude that it will have zero curvature everywhere. But now the thing is, if your space has zero curvature everywhere, that doesn't mean it's isometric to Euclidean space. I can give you a simple example. So, well, you all agreed that, I hope you understood that this flat space was isometric to this space, which means it has the same geometry. But if you sort of curve it all the way to get a cylinder, then it turns out that they are not the same. So what I'm saying is, this flat square is not isometric to a cylinder. Can anyone tell me why?
There exists a closed straight path on this regular but it exists a closed path on the sphere.
Yeah, that's good enough. So there exists a closed path, closed straight path. Well, actually you need slightly more than that, because when you say closed path, you could have a closed path over here.
Which is why I said straight.
Different
Straight,
geodesics.
so you mean geodesic?
Yeah.
Yeah. Right. So what you are saying is you can have a geodesic here to be a loop, but all the geodesics here are necessarily straight lines. And that is a good enough way to distinguish between them. At this point I could also introduce what the word topology means. So it turns out these two not only have different geometries, but they also have different topologies. And if two manifolds have different topologies, then they cannot have the same geometry. Because requiring two manifolds to be isometric first requires them to be homeomorphic, which means the same, which means they need to have the same topology first. And if I were to introduce topology to you, I would just say that, well, for geometry you were considering like a paper or just this napkin and trying to see if you can bend it and make something else. But in order to differentiate between topological things, I would like you to imagine like a blob of clay, and you can just sort of stretch it out however you want, but you can't tear it. And in stretching it out, you are preserving the topology of this piece of clay. So now, do you think a disk? Okay, by disk, I'll just say square again. Do you think this flat square has the same topology as a hemisphere?
Yes.
Okay, how many of you say yes? How many of you say no? Total sum doesn't add up to the number of people, but that's fine. So yes, the answer is yes, because if it were a blob of clay, we could just squish it. But do they have the same geometry? Yes or no? No. Yes, that's something we talked about before, because you can have angles here, you can have triangles here which have angles some greater than 180 degrees. But anyway, so I'll just record the observations that he has made till now. First observation was so first we found out the geodesics. And some loops are geodesics. Then she found out that sum of angles of a triangle is equal to 180 degrees. There are some geodesics which are not loops, because any subset of a geodesic is also a geodesic.
No, is there any geodesic that I can keep following that eventually won't come back to the same point?
Oh, right. That is a more involved question.
Is
Yes.
that an experiment he has done?
Not yet. Yes.
So geodesic is just the shortest straight path between 2 points, right?
Yeah.
So how can we call a loop as a geodesic? Because when we are forming a loop,
Yes.
the starting and ending point is the same point itself.
Yes.
So the shortest part would be like the displacement is 0. So how can we call
Right.
that loop as a geodesic if we
So that's a good question. Okay. So his question is that when that I defined geodesics to be the shortest path between any 2 points. But if I have a path starting at one point and ending at the same point, then how am I calling it a geodesic? So the actual definition of a geodesic is not just that it's the shortest path between 2 points. There is a more formal definition to it. But I can give you an intuitive idea of why I would call this a geodesic. And that's because, suppose I consider this sphere. So if T were on a sphere, suppose she started at the South Pole and she went to the North Pole. This is a geodesic, you agree, right? And now she can go back from the North Pole to the South Pole via geodesic. And if you look at this path as a whole, then it's smooth. So you can sort of, so I just want you to believe that whatever properties this path has are also shared by this whole loop. So it's just a continuation of each of these geodesics, and that's why I'm calling it a geodesic.
But in this you have described 2 different points also.
Yeah.
You stated that there are 2 different points.
Yeah.
But when we are talking about a single point,
Yeah.
so it will still be a loop.
So this whole path is a loop, right? It's going from here to here and then here to here. So I'm just calling it, I'm saying that, well, I'm saying you should probably be able to believe that this whole loop will have the same properties as half the loop. And half the loop is a geodesic. So it's just that the actual formal definition of a geodesic is not just it being a length minimizing curve. It's something, I can write it, but I don't think any of you will know what this is.
So it's like having same property throughout the path.
Yes.
But again, if we are taking the single point and we aren't displacing anywhere, we'll still be having the same property as we have started. We aren't doing anything in the space. We are just sitting idle there.
Okay.
It'll still be there and the property won't change.
Oh, so do you mean like a constant path? Like a,
We are just stationary, no movement. That would be a geodesic. Without displacement.
Hmm. If you have no displacement at all, yeah. Yes. Yeah, it would vacuously be a geodesic. Yes. This derivative thing will vanish because it's just a constant function.
And again, it's contradicting that we are having 2 way of same. One is
Right,
moving
yeah.
and one is sitting idle.
Yeah, but there the distance minimizing one is just the point one, right? Because that has zero length. So this thing won't be a distance minimizing geodesic.
Okay. So geodesics
So I was saying
vary according to the
there's a
property
unique.
we are needing.
Well, there was supposed to be a unique length minimizing geodesic, but yes, the point that you pointed out, I have to think about it. Yeah. So, yeah, these are the observations that T has recorded. So now the last observation is a kind of weird one. It turns out when T set out to make that journey from along a geodesic, starting from one point and ending at the same point, the world looked kind of different when she came back to the same point. So she actually started from her house, and when she came back to her house along the geodesic, things that were to her left were now to her right, and these flatlanders, they have a way of greeting each other. And so the way that they greet each other is they just rotate counterclockwise, and that sort of helps you see their shape. So it also serves as an identification of some sort. So just imagine this: if you were looking at a circle, in 2 dimensions, this is my circle. But as the circle rotates, this just stays the same, right?
Yes.
If now instead, if you have a square, what do you think will happen as the square rotates?
It stays the same, but the color gradient might change.
The what might change?
Color gradient.
Color gradient. Well, what do you mean by that? So you're assuming the square is not uniformly colored?
Maybe the bond.
No, it is uniformly colored, but then if you see the back parts, the shadow, that part comes here, it will be darker than the edges.
We're talking about a difference in depth.
Oh. I see. So you're assuming that there's some sort of light source and that it's shining more brightly on the parts of the square that's closer to you. That makes sense. But even if there was uniform lighting everywhere, I'm saying you will be able to. Yes.
The length will increase and decrease.
So for a square, what will happen is, well, initially if the square starts out like this, if you're looking at this edge, which has length 1, suppose, then the length of this line is 1. But as it rotates counterclockwise, its length will increase. So when it reaches this point, this is what you'll see as its length, which will be √2. and then when it's back in this position, it will shorten again. So, well, measuring exactly how much it changes by might seem weird to us, but flatlanders are used to it. So they can easily tell when someone is a square or someone is a circle, or a line is even easier to differentiate. If you saw a line in flatland, if they did a rotation, then at some point they would just vanish. They would disappear, become invisible. And then they would come back. And in the same way, well, if you had a triangle, then again there would be some sort of line which would grow and then come back, but the proportions would be different. So you will still be able to tell the difference. And when T came back home, she realized that her best friend, who used to look like this, well, she doesn't know that she looks like this. She just infers this by looking at the rotation. Now looks like this. She looks exactly like her. So what is going on? Does anyone have an idea? And why do you say that?
Because half like they rotate once and rotate this triple so T rotates.
Yes, so if you imagine a Mobius strip, if you imagine starting from one point and coming back to the same point along the strip, then it would be nice if I could draw a Mobius strip, but I don't think I can.
Paper they can just create.
Yeah, does anyone have a piece of paper that I can borrow? So in the meanwhile, if you know what a Mobius strip looks like, you can try and imagine what will happen if, say, the letter P, it starts out at a point on the Mobius strip and travels along the entire strip to come back to the same point once. What do you think it will look like?
So it will be inverted.
Inverted how?
Oh.
That's nice, but yeah, I think it might be too small. Can you guys see it? Oh, okay.
Also be small.
I think it's. Thank you. Yeah, again, I don't know if you can see it, but so suppose you just start out with this chalk and you go like this. So this chalk is starting out like this. Okay, can you see? It goes like this. Staying fixed like this. And and comes out like this. So this is the same point, because so the same issue again arises here. Because the strip is three-dimensional, it has two sides, so it's ending up behind the strip. But I want you to, yeah,
Keep going, it will come back.
sorry,
Keep going, it will come back.
yeah, but that's like making two rounds.
No,
Yes,
it's half the round.
sorry.
Haven't you made like half the round?
That's exactly what I want you to avoid thinking. This is one full round. Because this strip has no thickness. So if you just imagine this point and it traveling along the strip, it comes back seemingly behind the strip, but there is no behind. I'm saying the front is the same as the behind. So something that started out like this ends up here. So what's the main difference that you're observing? Right? Yes, it has flipped. So if this chalk were an arrow, if it were pointing like this, and after the whole trip, it's now pointing like this.
After 2 rotations, it will be back to the original shape.
Yes. So if we actually made 2 rotations,
So like in this case, it will again come back out, right?
yeah,
In 3 dimensions.
yeah. So you go like this, you go here. I'm skipping steps, but yes, you are in back. So this is illustrating something called orientability of manifolds, and this basically means that if you start out with a coordinate system at a particular point, so for a 2-dimensional manifold, if you start out with this x direction and the y direction, when you come back, if the coordinate is flipped, so if you go along the Mobius strip and you come back, what will the coordinate system look like? Yes, it will become this. So actually I should draw some different colors. So initially we had the white thing here. This is x, this is y, and finally we have the white thing here. And formally we would say that these two bases have a different orientation. These two so yeah, you've all taken linear algebra courses, and when yeah, so
I am not my first years.
oh oh my bad. Okay, I'll do you know what a basis is of a vector space? Okay, it's fine. You don't really need it. You just need to know that this ordering is like different from this ordering. And if this happens, then this path is said to be an orientation reversing path. And if a manifold has any orientation reversing path on it, then it's said to be non-orientable. And the Mobius strip is a perfectly good example of a non-orientable manifold. So all the observations that T has made
direction, or is it just for the entire surface we just call it non-orientable?
No, we call the entire surface
Entire surface.
non-orientable if it has a single orientation reversing path. So all these observations that T has made makes her somewhat confident that her the space that she's living in might look like a Mobius strip. But of course the catch is that it need not. And well, this is a problem in geometry, that often you can't say exactly what a space is just by looking at just by looking at its properties. You can't sometimes tell the exact nature of the space. You can't define the space concretely. But she's still satisfied with her observation, and she publishes them and wins the Nobel Prize, the Abel Prize, sorry, in Flatland. And yes, that's where I would like to conclude this. But if you have any questions, feel free to ask.
We were talking about how we can think of the Mobius strip as just a square and we sort of connect them
Yes.
like that. If we, so we said it's a square and then this side is sort of reverse connected to this
Yeah.
one, right? Can we also do it for the other sides? And
Yes.
so then what Mukund was saying, will it be orientation reversing in X as well as in Y?
So yeah, okay. I'll just draw what you have. Anyone who wants to leave can leave. So, you want to do this maybe? Or, yeah, maybe this one looks nice. Right? Yes, this is something called the projective plane. But yeah, what was your question?
So like in this one, does it orientation reverse in X as well as in Y?
No, I don't think so. Yeah. Well, so if you, the simplest way to see this is, if you cut this over here, then you'll get a Mobius strip, right? So if you start from here, then the same exact thing will happen that happened for the Mobius strip.
So suppose I have a line at some, so you had an arrow like this, it went that way, it hits the boundary. So then when it comes out to this side,
Yeah.
it gets flipped like this.
Yes.
That's your Mobius strip. If I have an arrow like this, and it sort of moves diagonally into the corner.
Oh. Okay. Yeah. So you want to consider a different path.
So then
Right.
it sort of becomes like this, and so it sort of flips along both axes, right?
Huh. So are you talking about like this part?
Yeah.
Huh. Yeah, this is a loop. So it has to be a bit more careful. No. So the thing is, the way I've drawn this, there's nothing special about the corner. because this is actually the same as this. This make it a circle, flatten out the corners.
She given a movie strip.
This is not a Mobius strip.
It's not.
But if you cut it in the middle, you get a Mobius strip.
Just like a diagonal, it's not. Like with the diagonal included, that shape they are making, that is not right.
With the diagonal included.
Like, why have you drawn that?
Oh, because Shida was talking about a path.
There's a path here.
Yes. Yeah, so I should think even if you take a path like this, it should be the same as taking a path like this. Because there's nothing special about the corner. So again, it would just be a normal orientation, reversing path where this will stay here, this becomes this.
Just changing the coordinate system.
Well, I'm just no. This is just a homeomorphism again. The topology isn't changing. Nothing about the space is changing. Try doing this. Yeah, I suppose. Yeah, geometry might change, but I think orientability is a topological feature. As far as I know, the orientation does not generally depend on the geometry of the space, but like purely depend on the topology.
So my question in some better words, the formula pi minus area of the triangle,
Yeah.
is that invariant and a metric? Like the area, we are defining the area using some metric, right? So
Yeah.
I figure that formula also depends on the metric.
Yeah.
So the area
But
that you're talking
what
about.
are you keeping fixed? What? So if you say it depends on the metric, are you assuming like a different metric that gives you the same geometry, or
For example, for Euclidean space,
yeah?
you could just scale the Pythagorean metric by some positive real number,
Sure.
and that gives you another metric on the same space.
Sure.
Something like that.
But those two metrics are like equivalent in some sense.
But the area still scales by a square. Like
Sure.
in the
Sure.
scalar
Sure.
space.
Yeah. If you have no further questions, or if you would like to ask me questions, you can. Yeah.
I didn't really count what my manifold is.
Oh, okay. So I introduced the notion of topology, right? So maybe using that will make it slightly more clear. So imagine a space which, when you consider a small enough neighborhood, so some weird space you might have, but for every point there is a small enough neighborhood in which the topology of this neighborhood is the same as the topology of some Rn. So if you want to consider a two-dimensional manifold, then every point will have a neighborhood whose topology is the same as R2.
Is it the
The-
dimension or?
Rn is the Euclidean n-dimensional space. So R3 is like what we assume we are living in. Oh, that's also an interesting thing. Are we actually living in R3? Is there some path someone can take in the universe where if they come back to the Earth, then they end up mirror reversed?
We should try one.
Yeah. And I have to be as motivated as Steve. But yeah, sorry. So, yeah, what is your question again?
Manifold. And
Yeah.
then I asked you what's Rn.
Right. So, just R1 is the straight line, the infinite line. R2 is the product of R with itself, so the infinite plane. R3 is again the product of R2 with R, which makes it the infinite three-dimensional space.
So can you say that manifold is same as dimension, number of dimensions?
The dimension of the manifold is the same as whatever Rn it is locally homeomorphic to. So homeomorphic means same topology. So if this neighborhood has the same topology as R2, then this dimension, if this is a manifold, then it will be two-dimensional.
And topology need not to be same as geometry.
Yes.
Topology can be.
Geometry you can think of some additional structure that you're adding to your topological space.
So topology talks about the space itself, and
Yes.
geometry talks about the properties which you can use on that space.
Kind of like additional properties you can add to the space, like distance, for example. An arbitrary topological space need not have any distance function, but Riemannian manifold, which is a manifold which has a certain geometry in it will always have a distance function. So you can always at least talk about distance between 2 points, and you can talk about angles. For a general topological manifold, you can't even talk about angles. And the length and stuff, yeah. Any more questions?
So, is there any difference between manifold and dimensions? Because like still in my mind it's the same.
Like, are you asking if a manifold needs to have the same dimension everywhere?
No, like does the definition of manifold and dimensions mean the same thing? Because in my mind it's similar to the same.
No.
And I feel like
The dimension is just a particular property of the manifold. Dimension is just a number which is equal to the dimension of the Euclidean space that it is locally the same as. So a two-dimensional manifold would be similar to R2 locally. A three-dimensional manifold would be locally similar to R3. But of course there is more to a manifold than just its dimension. Like you can have two different two-dimensional manifolds. A plane and a sphere are two different two-dimensional manifolds. They're topologically different and geometrically different. So yeah, if no one has any more questions, we would end this here. You can still ask me if you have any questions.
I think most probably कल भागते भागते पैर मार तब से तो